So when we're talking about enthalpy in here, enthalpy and thermodynamics, why do we even have chemical reactions, right? And so what's happening in the universe, this is the main theme of today, everything's trying to get to the lowest energy level possible. And that's just a good way to think about the whole world and the whole universe. Like, things are happening because we want to get to a more stable state. And so that's what drives chemical reactions. There are other ideas like free energy and entropy, but we won't get to those until Unit 7, like the last unit. So this is a beginning part of thermodynamics, and we'll hit the rest later. So heat is a form of energy measured in joules, and that's going to be that flow of heat. And so you should have got that on your quiz. Did you do that one? That was your give me. Merry Christmas. Thank you, Miss Freeman. I gave you guys a penny. On the penny, what did I write? A J. You want to guess what that is? A joule. Yes. And so temperature here is a measure of average kinetic energy. You should already feel very familiar and comfortable with that, yeah? Remember, when we're working with gases, we have to use Kelvin because it's the only temperature scale that is proportional to movement. When we're doing this, like calorimetry work, when we take little cups and we measure the temperature, all that formula has is a delta T, which is change in temperature. So if we go from 300 degrees Kelvin to 305 degrees Kelvin, it's the same as going from 27 degrees to 32 degrees, or 32 degrees. I don't remember what I just said, but let's say 5, so 32 degrees Celsius. So when we're doing these problems with calorimetry, we don't have to use Kelvin, but you need to understand that Kelvin is proportional to it. This is one of their favorite trick questions. Listen, are you listening? I'm going to keep telling you the trick questions, okay? They'll say, when the temperature goes from 30 degrees Celsius to 60 degrees Celsius, what happens to the kinetic energy? And you would think, since the temperature doubles, the kinetic energy doubles, right? Because 30 degrees Celsius is really 303 degrees. So that question really reads, if you go from 303 degrees Kelvin to 333 degrees Kelvin, does it double? No. So watch out for that. They really like that kind of question, okay? Only Kelvin is proportional to kinetic energy. You already know this. You should feel very familiar with this. The way I'm teaching you in order goes in a different order than these PowerPoints, and so I'm not going to go back over this, except to say that as we heat up a sample, a larger proportion of the molecules have a higher energy. I'm making a video. Is that for Abby? Cool. Go for it. So anyway, a higher part of the sample, and so we talked about that when we talked about gases. Again, the average kinetic energy is going to increase as temperature increases. This is a pretty straightforward little diagram here. We have a system here and a system here. If we were to put these together, what ends up happening, if you look at these little vector arrows on this first sample, you can see that they're shorter, which shows that they have less energy than the system 2, and they're at a lower temperature, 350 versus 450. And so if I put them together, they'll come to a thermal equilibrium, which is to say that they'll come to a kind of place where they have the same energy. And if you look at the overall length of these vector arrows, or how fast they're going, they end up averaging out, right? That's pretty straightforward. So anyway, energy can't be created or destroyed. This is the first law of thermodynamics. The second law of thermodynamics is you don't talk about thermodynamics. Yeah, that's funny. If you've been in AP Environmental, though, like, you know the first and second laws of thermodynamics. But in AP Environmental, I said, like, energy goes from awesome to crappy. That's the second law. And here, we're actually going to talk about entropy, and we're going to do math for entropy. But that's in November. I'll catch you around Thanksgiving, okay? If you wish, right? It's like, God, can we just leave it, like, awesome to... No? Okay. But the first law, you know, energy can't be created or destroyed. It's important when we're talking about enthalpy that you understand the difference between the system and the surroundings. When we're doing a chemical reaction, that's going to be the system inside the beaker or whatever. And then the surroundings will be the beaker, be the air, the classroom, the whole universe, literally. So the actual reaction is the system, and then everything, even the container it's in, is the surroundings, right? So if we're doing calorimetry, the styrofoam cup is the surroundings. Right? If we're putting if we heat up a piece of metal and we put it into water, right? The water is the surroundings. The metal is the system. That's why you have to flip that sign, right? If the piece of metal loses energy, it goes into the water. Water gains it. So you have to flip the sign. We'll get into that. That's tomorrow some more. We're not going to spend any time really on too much with this. Energy is just work and heat. Heat is work and work is heat, but whatever. There's a song that goes like that. But I am going to talk about this. So, you all have pennies with a J on it. And so you take your penny, right, and you are going to hand your pennies to your leader. Cool. Okay. Let's say your leader was the system. Okay? Everybody else's surroundings. You gave energy to the system. Okay? So, is that endothermic or exothermic? If you gave energy to the system, it's endothermic. Energy went into the system. Do you follow me there? You as an individual, as the surroundings, you lost energy, didn't you? You are now -1 joule. So the heat left the surroundings. And this goes back to what we had done earlier when I said if something's cold and you touch it, then that's an endothermic reaction because heat is actually leaving your hand and going into that system. This is the same. So if you gave your money to your leader, you're now colder. You have less energy because you gave energy away. And if we're taking heat, if we're taking and measuring that heat, that flow of energy, your leader would be warmer to the tune of 3 joules. How do you feel about that? All right. So anyway, kinetic energy is heat, is temperature, right? So if you have endothermic, the kinetic energy when I start is quite large, right? Because it's hotter than when I'm done. Now it's colder. The kinetic energy, which is temperature, smaller when I'm done. Okay, so the bonds in the products contain more potential energy. So this is my reactants or my reactant, and these are my products. The bonds and the products have more potential energy and less kinetic energy. And notice here my enthalpy value is positive. You gave your leader pennies, so the system gained enthalpy, gained heat. And in this class, like enthalpy and heat, the only difference there is like we have to be at a constant pressure and volume, and for this class we will do that. If you're taking AP Physics next semester, that's not, you'll do that there. Have fun with that. So we don't have to worry about that. Anyway, so heat goes from the surroundings into the system. And so the products are going to be at a lower temperature than the surroundings, right? Your heat is coming in from the surroundings. Anyway, and that'll continue to happen until equilibrium is reached. If we're talking about an exothermic reaction, we would expect, look at the kinetic energy. The kinetic energy in the products is an exothermic reaction. So now your leader give the money back to everybody. The leader again is the system. You're the surroundings, right? So what is going to happen to the temperature of the surroundings if you just got money? You're going to get hotter, right? The energy flowed out of the system. Your leader is the system. So now you're warmer, and the actual system has lost energy. So anyway, so you can see the kinetic energy goes up with the exothermic reaction. We would expect that because the temperature goes up of the surroundings. So anyway, heat again leaves the system, goes into the surroundings, and so our enthalpy value, your leader just gave away the money, right? So the enthalpy value is negative H. How do you feel about that? All right, cool. That's the easy part for today. These work and pressure and volume calculations, I've talked to a few people, they said don't worry about this. I taught it last year, it was never on any test ever. So I'm skipping this part. Skipping. Okay, this is the part I want to talk to you about. Listen, on your formula sheet, if you look at your formula sheet, let's talk about it, because this is, I talked to somebody last period, and this is, I've already been to this party. I've already been down this road. You have not, just trust me. The formula sheet is very misleading for this unit. So look under thermodynamics, is basically up under the gases and stuff. You had the questions on the, I like to call questions on the MCAT formula. MCAT is the test you have to take to be a doctor. Q equals MCAT. You see how it looks like an MCAT? That's, I mean, you have it, so you don't have to have it memorized, but like chemistry and Olympiad, it's not on there. So, anyway. That's fine. And then you have entropy, that's S, we'll get to that later. And then there's your enthalpy. And notice it's the enthalpy of the formation of the products minus reactants. This formula is not in, this has nothing to do with what we're talking about today. This formula has to do with where you have to add all this stuff up and cancel it and everything. This is not today's work. This formula really is almost useless. The stuff that's on the, they don't test this law and stuff, I've not seen a question about that. What we're doing today is all over the test. And this formula, if you use it for today's stuff, your answer will be exactly backwards. If you use this formula on your quiz for the bond energy question, you got it exactly backwards. Alright? So notice how this has delta H sub F, that's the enthalpy of formation. That's not a bond energy. That's like that chart that has, you know, things that from their elemental stage, blah, 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 mess. Okay? So really, the formula sheet for this unit is pretty much worthless because you can remember questions on the MCAT, and then that enthalpy thing is only for the values of, you know, formation. So, having said that, I'm going to show you how to do this using your head. You don't need a formula sheet. Okay? And it worked out really well, and I think we're gonna do this. So, anyway, moving on. Okay. When we were talking about our magnets, okay, everybody got two magnets? Thanks. So we know that when we form a bond, energy is what, everybody? Released, and we know when we break a bond, energy is required. So I want you guys to look, here's the burning of hydrogen fuel. Okay, let's just look at that first reaction. Okay, what I want y'all to do is talk amongst yourselves and figure out, are the reactants themselves, the hydrogen and the oxygen, are they going to be coming together like this? Are they going to be bonds made? Or are they going to be bonds broken? Bonds made or bonds broken? Okay, and then after you figure that out, is that required energy or release of energy? So figure out products and reactants. So I want to know bonds breaking, bonds forming, enthalpy positive, enthalpy negative. Reactants, products. This is all on Schoology or just in unit 2? Alright, you guys got it? Maybe. So the hydrogen and the oxygen first. So where are the bonds being broken, Talia? So you said the hydrogen gas and also so we also break in the bonds in the oxygen too. Yeah. So these are bonds broken. Do you understand that if I have oxygen and hydrogen floating around the room, I can't make water until I break apart the hydrogen and oxygen, right? Okay, cool. So I don't know. I put an S on that. Whatever. Enthalpy of bonds being broken. Positive or negative, Kat? Do you have to put energy into breaking bonds? So if you have to put energy into it, then it has to gain energy, which is positive. Okay? So right, this is breaking the magnets apart. You have to break them apart to rejoin them into something else. Alright. So these are obviously, I mean, if I ask you, are bonds broken or formed? Obviously the water's formed, but you have to take that time to think about it. So these are bonds formed. being formed releases energy. If you release energy, that's negative. Do you understand? So, I just lost, I'm negative 1 penny right now. Negative 1 joule. So, this is negative delta H. So, overall, look at me. What this tells me, do you see on this first reaction how the enthalpy is negative? What do you suppose is true? Was more energy going into being broken or more energy released when it was formed? More energy has to be released when it's formed because overall it's a negative enthalpy. That negative number, these negative numbers have to be bigger than the positive numbers because this number's negative. And if we happen to switch this around and do the reaction the opposite way, y'all know this from your homework. If you reverse a reaction, you change the sign of the enthalpy, right? Y'all figured that out. And I know you may not know everything when you're getting done with homework, but you'll know like the basic stuff like that. And so you would think, and that makes sense. Again, this is positive, so the energy from breaking the bonds is larger than the energy released when the bonds were formed if you reverse it. Can y'all kind of conceptually follow me there? All right, the number's negative, then the numbers negative had to be bigger than the numbers that were positive. Moment of silence. How you feel? Okay, remember bonds have to be broken. That takes energy. You got to take energy to break apart a magnet. That's positive. You got to put energy into it. To form bonds, energy release. Energy comes out. Like you lose money, you're negative. Okay. I'm doing like the best I can to make this as concrete as possible. No math yet. How do you feel? Okay. It's about to. Okay, so this is not so bad. When I go from hydrogen and oxygen to water, energy is released. If I go from water to hydrogen and oxygen, then energy is needed. So that's not that bad. No problems there. So there's 4 ways of finding the enthalpy of a reaction, and today we're doing one of them. Why does this even happen? Why do we even make bonds? Because, and this is what I was talking about a minute ago when I was talking to Devin, right? This attraction between these 2 atoms, that is a high potential energy, and the universe is going to work in a way that it's going to try to get to that lowest energy state. So if they come together, you're going to lower that potential energy, and then this bond will be formed. And high potential energy, right, if I hold something up and I let it fall, high to low releases energy. And then that would be, if I drop the pen, you can hear the sound waves, there would be an impact on the board, etc. All right, so enthalpy. This is, if you don't learn anything else today, energy is always released when you form a bond, always. Energy is always needed to break a bond. And think about the magnets, always go back to that. What ends up happening with exothermic reactions or endothermic reactions, the energy won't ever be 0, right? Like, why would the reaction go through if it was 0? That doesn't make any sense. No, nothing was changed. But the reason, when we get to entropy and free energy, that'll make more sense, and we'll go into the details of that. But when we're looking at that, and we have a negative or positive numbers, the energy needed or the energy released was more or less. All right, so this is the reaction pathway. We'll get into these more in Unit 5 with kinetics. But let's just look at this real quick. You know when you're doing the Hess's Law problems, you had to add all the reactions up and like play the puzzle game? Yeah, that was fun. This is one step of the reaction, and this is another step. And these are like the little things that add up together. But they don't even need to understand this yet. Look, you had to break this bond, and then we had to make a new bond. See it? Overall, if this this y-axis is showing energy, right? Overall, talk with your neighbors and discuss if this is endothermic overall or exothermic overall. Okay, so endothermic would tell me that energy overall went into the system. If this is where I start on my energy, and this is where I end, yeah, so this is exothermic. So look, this is the thing. All reactions need energy to get started because you have to break a bond. So look, I had to take energy to break that bond. You always are going to have this like roller coaster uphill thing. That's the activation energy. We'll get to that later. But that's the energy going into breaking the bond. But look, when those new bonds were created, they release more energy than it took. This is going to be exothermic for that reason. This part doesn't really, this middle part doesn't matter for you right now. So it's exothermic because energy is released. But that's why you always got to put energy into it. But sometimes the energy that's released is more than what you put into it, and that's where you get your exothermic. An endothermic reaction pathway, if we wanted to show you endothermic, it will look like this. See, energy overall was greater when you ended. Energy went into it. That's the difference. Okay? But you always have this little hump to get up. Activation energy. Okay, so exothermic reactions, and this is what I was just telling. Look, do you see this formula? If you do, you don't see it. You don't see that formula. It doesn't exist. There's not a formula for this. This formula is not on your sheet. If you think there's a formula for this, you're going to use the formula on your sheet, and then it's going to be exactly backwards. Because bonds broken, guess what that is? That's products, isn't it? Bonds formed is reactants. Look at the formula on your sheet. Which one goes first on that? It's products, isn't it? This isn't a formula. There is no formula. We're not using a formula. We're using our heads, and it'll make sense. Anyway, so exothermic, again, more energy is released than required. Endothermic, less energy. So let's get into this, okay? Go ahead, you probably want a piece of paper. If you just want to watch me this first time, that'd be fine. I'm going to switch over to the other board to give myself some room. But I have methane. This is a combustion reaction. What would you expect the enthalpy to be? Positive or negative, everybody? A burning methane. Negative, because heat's released. This is how you cook food. Yay. That's natural gas, right? Now, most of you guys had chemistry last year, and you know how to draw Lewis structures. Some of you don't. That's okay. I'm going to teach you from the very beginning how to do Lewis structures, but that's next unit. So as we do this, I'm going to draw them and kind of talk you through them a little bit. But as you're doing your homework and stuff, if you don't know how to draw a Lewis structure for methane, just Google it. I don't care. I'm going to show you how to do it next time, okay? But the thing is, there's just so much required to get started with this class. I can't even go in an order where you don't have to know something when we start, right? So, let me bounce this equation. I need a 2 here, and then I need a, is that it? Okay. So we have these values. That chart that was just there, those are the energies in these bonds. So I have to draw these things to count up and look at the bonds. If you get lazy and you don't feel like drawing them, guess what you're going to do? You're going to screw up. You know, I'm speaking from personal experience. So, anyway, these here, my reactants, this is bonds broken. What is that, positive or negative enthalpy? By breaking a bond. Positive. So this is my positive enthalpy. So these numbers are all going to be positive. Over here, the stuff I'm putting them at the magnets are sucking the stuff together and they're releasing energy, right? So this is going to be my negative enthalpy. I should wrote it like that up there. So again, all these numbers are positive, all these numbers are negative. When we get done, right, we're going to see, we're going to have these two sets of numbers. These will be positive and these will be negative. If the negative numbers are bigger, when we add them up, our answer will be negative. Positive numbers are bigger. When we add them up, the answer will be positive. It's not a big deal. Okay, so let's go ahead and draw this out. Methane is a tetrahedral. If I taught you last year, you know this. Yes? Do you know this? Sort of happened. And then oxygen, when you're drawing the diatomic molecules, like Wrinklehoff, when I say Wrinklehoff, does that ring a bell? However many valence electrons they needed is how many bonds they had. So oxygen needs 2 valence electrons because it has 6. Okay. So this is methane plus 2 oxygens. That's what I have right here. Okay. And then a carbon dioxide is a double bond between the carbon and oxygen. I have one of those, and then I have 2 waters. Okay. Now what I'm going to do is I'm going to add up these bond energies, and what I'm looking for is I'm looking for my phone because I took a picture of the chart. So excuse me for a second. I'm going to actually text some of that now. I don't even have friends. I'm not going to lie. Y'all are like, yeah, probably right. No. Okay, sorry. Do y'all's phone ever just start pushing buttons and then you can't really do anything about it? That is happening to me right now. The heat? The enthalpy? Is it the enthalpy of it? Alright, anyway, so I have, this is the hard part, not really, but this is where people mess up. I have 1, 2, 3, 4 carbon hydrogen bonds. On your PowerPoint, those are 413 kilojoules per mole, right? So I have 4 carbon hydrogen bonds. So I have 4 times 413 kilojoules per mole. That equals 1652, I think. Okay. Then I have 1, 2 double bonds between 2 oxygens, and that is 495 kilojoules per mole times 2. So I guess that would be 990 kilojoules per mole. So all of my bond energies for all my reactants is going to be 990 plus 1652. So that should be 2642. And this is a positive number. Have I blown your mind with this? I know when you're doing your homework, you're like, I have no idea what I'm doing. Feel better already? Alright, so I have 1 carbon dioxide, and I have 1, 2 carbon oxygen bonds, and they're double bonds. So that's 799 kilojoules per mole times 2. So that's 1598, because it's almost 800 times 2, right? And that's negative, and this is negative. And then I have 1, 2, 3, 4 hydrogen oxygen single bonds. And those are 467 kilojoules per mole. What? Oh, I'm just using the chart on PowerPoint. So that times 4. I'm not that good at math on this one. I guess that'd be what, 1800 and something. What is it? I'm sorry.
1868.
And it's negative, right? And that's negative. So I'm gonna add up these numbers. I'm adding these negative numbers. So that gives you 3,000 and something. 34, 34. Negative 34, 66. Yeah, okay, I'll love it. So listen to me. To find the enthalpy of this whole reaction, there's the energies in the bonds of the reactants. Energy released during the formation of the products. And now I'm just going to add these numbers together. Right? You can already tell this is exothermic because the negative number is bigger. Yeah? So I'm just in my calculator, gonna go 2642, and I'm not subtracting. I am adding a negative. I know math, but listen to me. Look at me in the face. If you think about subtracting the products, do you know if it's exothermic, it's gonna be negative. If you think of subtracting, what are you gonna end up doing? Subtracting a negative, and guess what? You're gonna add it. And then so listen to me. and the reactants and the energy of the products, you're adding a negative number. Don't think of subtracting because then you'll do minus. You'll do this crap. You know what I'm talking about? Don't do that. You can do whatever you want, Christian. Hush. This, like, just trust me. Okay. So anyway, I mean that super nicely, but I've been to this party and it's not pretty. So anyway, the overall enthalpy of the reaction is invisible. What is going on? So it's negative 824 kilojoules per mole. You just take your two numbers and you add them up. All the energy in the reactants, all the energy released during the formation of the product. Deal? It's not the worst thing that's ever happened, right? Okay, so I want you to try one of these before I keep going. On the practice problem, I think it's number 9. Try that by yourself. Because there's more to this. Just a little bit more. Yes, sir. Yeah, you can use a whiteboard. That's fine. Oh, well, if you use a whiteboard, these are your practice problems. So you might be sad about that. So, not on this one. Christian, I gotta know what you're saying. You can tell me, just me. Tell me just like use the formula where you subtract it. Look, yeah. So let me show you. If you get it, that's fine. But let me show you what I'm trying to say. If I teach it like that, look. If I teach it like that, that.
The other one's like the reverse.
And so here's the formula. Here it is. And that's what you're saying. But it's not worth it. Been to the party. The people that teach this, that have like 80% of their students make a 5, that's where I'm getting this idea from. I didn't make this up. I would like to go to 80% of my students make a 5, or 8%. I would be down with that. Is it number 9? Let me see. Can I see somebody's practice? Yeah, number 9. Do y'all need me to draw the Lewis structures for you real quick? Okay. We're going to get to that next unit. Okay, so I have nitrogen. So nitrogen, how many valence electrons does nitrogen have? It's 5. So it needs to make 3 bonds. So I have nitrogen and then hydrogen. And I think it was 3 hydrogens, wasn't it? Hydrogen needs 1 more valence electron. So I'm drawing 3 of these. I don't care. Like, it's not. You know what a waste of your time is? Doing all this and messing up. This is not. That took me 5 seconds. Not even. And that gives me, how many ammonias? 2? Alright. And then the cool thing about drawing it is you can check your work, right? Because you can, like, see if it bounces. And this has a lone pair, whatever. I'm real into showing my work. I like that. And here. That makes me feel better about my life. Now y'all good? There's a chart for all the enthalpies of formation at the end. Some of the questions are like solve for the enthalpy of formation. I know it's just hard. It's still that. Yeah, I got it. I follow. Hello. I'm gonna. Me too. Okay. Okay. That's fine. All right. No worries. If I ever work for lunch, I'll do that. I eat at the priority. As y'all are working working this out on the board. Is anybody done? Can you tell me the enthalpy values or bond energy values?
I just.
Okay, I'll start the work up here. Then you can.
That part.
Andrew, what's a triple bond of nitrogen? Alright, what about hydrogen single bond? How many? And then the nitrogen hydrogen? 93? 393. I thought so. That's low. Okay, cool. Thanks, y'all. Am I doing magic tricks on the board? How you feeling?
That's all we're doing today, like this stuff.
Yeah, I have to, there's one kind where like you don't know the bond energy of hydrogen, and so like you're given the enthalpy of the reaction though. That's the last thing we'll show you today. Did y'all get 71? What did y'all get? You didn't get that?
No, yeah, I got -1.
Did I not multiply this? Is this, there's 6 of those. Is this number right? Did I push buttons on my calculator wrong? 6 times 393. Oh, I did 363 because I just did it again. 20, that's so weird. I'm sorry. 23, 58. My bad. So negative 109, how about that? Better? Okay, I'm about to have a heart attack. But you know, if you show your work like this and you have it drawn, like the work and everything was going to be a point and that's going to be a point. But if you just have a bunch of slop on your paper and then you get it wrong, you get nothing. So, life skills. Okay, how are we doing? Do you get my ideas? Like, on the test when you don't have a formula sheet, right? Okay. Can you remember, okay, the bonds in, when you make the products, they release energy, so they're going to be negative. The energy in it that's broken, that goes into breaking the reactant bonds, that's positive. And then you just get 2 numbers and you put them together, right? So, not too bad. So we're just trying to be a little more conceptual. All right, the last thing I have to show you is what happens if you don't know a bond enthalpy. In some of your practice problems, you don't know the bond energy. Like, so this one, it says, calculate the average bond energy in a hydrogen-hydrogen bond. Yes, look, I know that on your homework, it has the hydrogen bond enthalpy. Like, I'm aware of that. Cool. But if you didn't have it, how would you solve for it? So this is pretty straightforward. I'm going to go to the other board. Y'all got to help me out with these numbers. So hydrogen and oxygen gives me water. So going over here, I did it again. That's like an owl or something. Hydrogen, and then there's the oxygen. Okay, how do you feel so far? Haven't done anything crazy. So, this is what we're solving for. So basically, 2 times x, right, plus 1 times, what's the bond energy of double oxygen, you guys? Okay. And then I have 1, 2, 3, 4 hydrogen oxygen bonds. And what is that? Okay. Yeah, I mean, they're not going to give you something that's impossible to solve for. But in this case, this is going to be a negative number, right? I feel like we just did this 4 times this a second ago. It was 1800 and something. So, anyway, 2x plus 495 kilojoules per mole. Somebody push the buttons in their calculator and tell me what this is. Negative 1868. Thank you. Sounds familiar now. And all that, so basically 2x plus 495 plus a negative, right, plus a negative 1868 equals, and then the energy for the whole reaction, was how many joules? Kilojoules, I should say. How many? Negative 572. So this plus this plus this has to equal negative 572. Can you solve for x? Yeah, you sure can. So what you're going to do is combine your like terms. Here's your like terms. So go ahead and combine those. You have positive 495 and negative 1868. I'm going to erase my little line here. So I have negative 1373 kilojoules per mole. 2x minus that is equal to negative 572 kilojoules per mole. I'm going to have to isolate my x. I can do that by adding 1373 to each side. So negative 572 plus 1373 gives me 801. So 2x equals 801. So x equals 400.5, and it has to be 401 because it's 6 bigs on 3 seconds. That's so bad? Cool. So there's several that you can skip in your homework. Let's talk about those. If you pull the homework section off of your shoulder, that'd be awesome. So we already talked about Maxwell Boltzmann distributions. We are very comfortable with that, yeah? So y'all can skip number 1. Y'all can skip 4 and 5. So 1, 4, and 5. You can also skip 6, 7, and 8. And then I need you to do the rest of them. So you don't have a whole bunch. But you'll probably have a little bit more tomorrow. So you might want to, you have about 20 minutes. You can probably get most of that done. But tomorrow you'll have more to do and you'll have a big answer, okay? Do you guys want to tape the answer key? Okay. Let me stop the video and I will do that for you.